So to start this up, actually I already recorded the video thinking that this topic was already taught, and then realized it was not taught yet. So this needs to be taught before the rest of the video because I use it for the rest of the video. To start us out, we have this idea called critical values. Critical values. Well, this is an idea regarding a function and its derivative. So a critical value happens whenever the derivative is equal to 0 or doesn't exist. When f of x is equal to 0 or, oh, or not of, or, sorry, derivative, so f prime is equal to 0, or f prime of x does not exist. Right? So the critical value is when that happens, aka the x values, right? So these correspond to the derivative being 0 looks like our horizontal tangent lines, right? And then the derivative not existing maybe corresponds to like a piecewise function. So maybe it goes up like this and then over like this, and then at this point the derivative would not exist. So if this is an x value of 0, maybe this is an x value of negative 2, and the critical value would be at x equals negative 2 and 0. Critical value. So this is just our definition, right? Critical value means the derivative is equal to 0 or just straight up does not exist. So we are going to use this for maybe forever. Definitely for the rest of the majority of this chapter, right? It's really important to know when functions equal to 0 or does not exist, right? Because saying, right, the first things when we look at functions like 1 over x is, well, where does this not equal to 0? Sorry, when does this not exist? And the first thing we ask when we look at polynomials, right, when, oh, 2x minus 1 is what I wanted, 2x minus 1. And then the next thing is looking at when these functions, polynomials, right, are equal to 0. So critical values are kind of asking those two big questions about the derivative of the function. So there's a critical value of x when the derivative is equal to 0 or the derivative does not exist. Very good. So this section is, or this chapter is going to talk a lot about graphs at the start. So right away, let's say we have some function that looks like this, right? This is my x and y axis, and we have our function f of x. Well, the first thing to try and talk about that, is of value to us is maybe this function is graphing the profit of some business at some point in time, or like the value of a stock, maybe even, right? Then in those contexts, it really makes a lot of sense to try and know when we have a maximum value, when the function is at its highest, right? So in so many contexts, right, we want to know when is this output going to be the largest it ever will be, or maybe the smallest it ever will be. So for that reason, we like to talk about maximum values. And so this section is going to introduce a lot of ideas about handling and interpreting these maximum values, but we also sometimes care about minimum values, right? So sometimes we have maximums, sometimes we have minimums, but either way, these are extreme values, right? If I want to refer to something that might be a maximum or a minimum, right? But either way, it is extreme. Then I'll refer to these as extrema or extreme values. Extreme values, right? Well, for this function visually, we can see that the largest it ever goes to is up here, right? So maybe this number is like 20. Well, if I, again, oh, 2, 0. Well, that's if I look at the function as a whole, right? So, well, just in the same way that I can say that this function has a max of 20 is the maximum value of the function, but it's really important to know at what x value does that happen at. So maybe I'll say 5. So maybe I'll say it has a max value of 20 at x equals 5. Because if we're interpreting these things, it's just as important to know when that value happens at, so like what is the x value, as much as it is to actually know what that maximum value genuinely is going to be. However, in this context, right, we can see that it has a maximum here, but what about a minimum? Does f have a minimum, right? Is there a lowest value that this function achieves? And we would say no, right? Because we can interpret by the arrows, not only all the way to the left, but also all the way to the right, that the function is going to keep going lower and lower and lower. So for any value that you give me, maybe negative 10 billion, I know I'm going to keep going lower. I'm going to have 10 billion and 1, negative 10 billion and 1, right? So there is no minimum value, which we can see that visually just by looking at this graph. Well, in the world of functions, sometimes we're not able to see the entire function at once. Sometimes we're only looking at specific values in a specific region, right? And whenever we talk about critical values or whenever functions have horizontal tangent lines, then if we ask that for this function, where does this function have critical values, aka a derivative of 0, again, aka horizontal tangent lines, right? A flat tangent line here. Well, the tangent lines are going to track like this, like this, like this, and then we are going to flatten out on this peak. And then we're going to go down and down, and then we're going to start to flatten out again at the bottom of that part there. And then it increases once again, and then we kind of really suddenly flatten out up on this hill, and then we go down again, again, again. So again, I'm just tracing, right, the tangent lines along the function, which is just sticking some flat lines along, right? But I notice that I have 3 critical values, 3 instances of a horizontal tangent line. And I didn't mark what those values actually were, and I don't really want the whole graph to be covered with the red line, so let me undo all of these. So if maybe this one happens at, we can say -5, and this one happens at 0 at the origin, well, I have my flat tangent lines, my critical values, right? 3 of them. Well, I kind of noticed something, right? If my function has this maximum value, then that kind of demands that I have a flat horizontal tangent line almost, right? Or at least that my derivative kind of hits off to being 0 here with this nice and smooth function like this. Well, notice something, right? the shape of the function, everywhere that I have these flat tangent lines, kind of looks similar. And if I zoomed in enough, right, so that I maybe couldn't see the entire world that this function is, then, well, just right here, it kind of looks like I might have an actual maximum value here, right? This looks like a max, like a maximum. And we might even say that locally it is a maximum. And similarly, if I just zoomed in far enough, this looks like a minimum. And locally speaking, if this was all of the function that I could really see, was this neighborhood around, oh, yeah, sure. If what we have right here is all the function that we can actually even see inside this yellow box, then yeah, that would be a minimum value inside of that yellow box. And similarly, if all I had was like this bit, then this earnestly does look like a maximum value for the function. And so, and well, it's definitely true that if I drew a box around the genuine maximum of the function, then it still looks like a maximum even just inside of that box. So for that reason, we actually do make this distinguishing fact, this definition of local extreme values. Local extrema, which again is just that word that we're using to refer to maximum or minimum values, are extrema in a region around that point. If I were to confine myself to that neighborhood, right, around each of those points, then it looks like I am a maximum or a minimum value. Now, that is different from being the actual maximum value of the function, right? It looks like it is, and certainly it is a candidate to be so, but that doesn't mean I am the maximum value of the function. So we want to distinguish between these new local extreme values and these extreme values that work for the entire function. So instead of saying local extrema, I want to say it's the genuine extreme values, then I would say those are global. And another word is absolute. So they are global or absolute extrema are the highest or lowest values the function does achieve. So here in this example, it is certainly true that I have local extrema in each of these yellow boxes, but I only have one global extrema. There is only going to be one genuine highest value the function ever achieves. And again, is there actually a global minimum? Still no, right? So this function has three local extrema, and we said that they happened at x equals -5, x equals 0, and x equals +5 in this example. However, one of these local extreme values is also a global maximum. Glo global max, and that is at x equals 5. And really, if I wanted that maximum value, I want the y value, right? I want to know where we actually achieve that value. But here, I'm just saying the x value, right? Really, the global max is y equals 20, right? The coordinate might be more useful here, 20 comma 5. That's carrying the most information, right? Because if I said, when does this, or sorry, if I said, what is the highest value that the stock will ever achieve, and you just told me 20 days in, well then I don't really want to know maybe when that happens. I said, what is the maximum value? I want to know what the value of the stock is, not just the time that it occurs at. So, oh, hold on. I don't know why I wrote the x and y value backwards like that, right? That's 5 comma 20, right? If I say what is the maximum, I want the y value. But if I say it happens at, or when does the maximum happen, for what x values is that achieved, I would say x equals 5. What x value do we have? These extrema, -5, 0, and +5. Again, that's just very specific to this function, right? Some functions may never have any extreme values. So take, for instance, just y is equal to -3x plus 1. Just a basic line. What is the max? Or sorry, I went to put a question mark there. What is the maximum value that this function achieves? Well, we're going up to positive infinity all the way to the left, so there is none. Or we could say infinity, right? It increases that bound, but when I say what is the maximum, I'm expecting a number, right? So it's really not going to be infinity. It just goes up forever and ever. Is there a minimum? Well, no. I'm also going down and down and down forever, so there is also none. But even more so, if I just picked some point, right? If I at least wanted local extrema, does this function have any of that? Well, no, because if I zoomed in, so if I zoomed in on this function, right, at this point, and I tried to write some box around it that I could maybe hopefully achieve the maximum value of, well, what am I going to look like? I am still just going to be some point in the middle of a line, right? I'm trying to like draw what it looks like when we zoom in, but when we zoom in, we still just look like some point along a line. Is this point the maximum value in this neighborhood here, not a maximum or a minimum? This is not extrema, and that is the most garbage font or handwriting that I've ever had. Uh, this is not an extreme value. E X T R E M A. It is hard to write when you're zoomed in like that. Right. So, is there any local extrema? No. none, even. Right. So again, this actually ties directly into the conversation that we had before about critical points. So if we recall our definition of critical points, we have critical points of f of x, x comma y, or we'll say x naught comma y naught, right, for a specific point, a specific coordinate. If f prime of x naught, right, x naught y naught is a critical point if the derivative at that point is equal to 0 or does not exist, right? Because if our derivative is equal to 0, then our function flattens out somehow, which is indicative of maybe we are going to be a local max or min. Because if our derivative changes sign to be negative after that, then yeah, we've achieved a local max. However, what happens if instead of our derivative decreasing, what if our function kept going up again? Well, now my derivative flattens out, my derivative is 0, but am I a local extreme value? That answer is going to be no, because whatever window I draw around the function at that point, right, I'm zooming in right here, my function is like that there and like this here, I don't actually get to be the highest or lowest value in that window. Because to the right I am increasing, and to the left, right, or sorry, on both sides of the function, of both sides of the point, the function is increasing. So kind of just like the situation with the line, no matter how much or how I zoom in, I don't get to look like the highest or lowest value in that entire window, right? Looking on both sides of that point, I don't get to do that. However, it certainly is a good place to start to ask where a critical value is. And it turns out, right, looking at all of my local extrema that I had here, my derivative has to be 0 wherever I have local or global extrema. So one way of looking at this kind of situation is with kind of a Venn diagram that I like to draw. So if I wrote this big circle for all the points that the function exists for, and this big circle for all the critical points, then inside of this circle, we're going to have local extrema. These are all the values, right, that we zoom in and it looks like a local maximum or a minimum, right, inside of that neighborhood. So my critical points are candidates for local extrema. Well, then local extrema are also going to be candidates for global extrema, right? Because any global extreme value, it certainly is true that I can draw a circle around it and it turn out to have some, right? And it turn out that it is the biggest or smallest value in that neighborhood, right? So if I, and there's an analogy that I like to make, if you are the best in the world, you certainly are best in your town, right? So if you are the global champion, you certainly must be the local champion. And that analogy also kind of extends to the critical points thing. Any local extrema also has to be a critical point, right? But if you are the best in your town, you are also just a candidate to be the best in the world, right? You can't win on the global stage if you can't even win in your own neighborhood, right? So critical points say that we might be a local extreme value and local extrema might be global extrema. So I'll say this, I always like to write this piece down, that critical points are candidates for local extrema, which are candidates for global extrema. Right. So if I find a critical point, it might be a local extreme value. And if I find a local extreme value, it might be a global extreme value. So the next thing to do is try and look at some of these examples, or some practical examples that look like the problems that we would want to work out here. So let's take this example. Find and classify extrema of f of x equals x squared minus 25. Well, first of all, in order to answer that question, we want to find critical points, because these are our candidates for local and then global extrema. So in order to find critical points, we need to take the derivative of this function. Well, the derivative of x squared minus 25, we look at in pieces, right? Derivative of minus 25 is plus 0 or minus 0, right? Subtract or minus 0 doesn't do anything. The derivative of x squared is 2x. So in order to find critical points, we want the derivative to be 0, which really means we want to find values where 2x is equal to 0, right? 2x is our derivative. We want to set that equal to 0. Well, hey, how do I solve for 2x equals 0? That means x is equal to 0. Now, technically speaking, we also want to solve for when our function does not exist. Sorry, our derivative doesn't exist. Well, does the function 2x ever not exist? No, right? This is a perfectly fine and easy function to consider. So we have one critical value at x equals 0. So the next thing that we want to do is classify this critical value, which just means say, right, my critical point is this. Now, is it a local or global max or min, right? Tell me, is this critical point actually going to be an extreme value? And if so, tell me what kind of extreme value it is. Well, the thing is, we know what this function looks like, right? This is a really nice example. This parabola faces upwards and has two x-intercepts, right? It's going to be 0 when x is 5 or negative 5. So drawing this graph is actually surprisingly easy, right? My y-intercept is at negative 25, and then I'm an upwards facing parabola, and I intersect here and here, right? 5 and negative 5. So when x is equal to 0, can you tell me what kind of extreme value we have? Well, that has to be, is it a max or a min? Well, it certainly must be a minimum. Is it a local or a global? Well, I see that as the lowest the function ever goes. So that is a global minimum. So I would say the right coordinate 0, comma, negative 25 is a global minimum, right? That is the lowest value the function ever does achieve. Well, the next catch here is that technically speaking, a function can have a global value at multiple x values. Well, that feels weird, but let's look at this example. I'm not going to come up with a function for this because those get pretty weird, but let's say I have a function that looks like this, right? Where both of these x values correspond to a y value of negative 5. Well, let's say just looking at this, let's find and classify extrema. Well, okay, the easiest thing to pick out would be our global minimums, right? Our global max or mins. Well, I noticed that the lowest the function ever goes, right, because we go to infinity on the left and right up here, the lowest the function ever goes is happening at these two x values. So I have global min, that minimum value is negative 5, but that happens at x equals negative 2 and at x is equal to positive 2. This is perfectly fine, right? All I'm saying is that the lowest this function ever goes is negative 5. But I also want to know where that happens, and that does happen twice. So it is the lowest, there's one lowest value that that function ever achieves, but we get that with two different x values. And that is okay. It is still a global minimum. It just happens twice. Well, now do we have any global maximum? Again, no, we go off to infinity on both sides. Do we have any local extreme values? So maybe a local max or min. Technically speaking, our global minimums are also going to be local minimums, but we don't want to repeat ourselves, right? It's not really useful to say, by the way, these are also local minimum values. So that is true, but because we're classifying each extreme value, we're going to call them global minimums and then not repeat ourselves by also stating the fact that they are local minimums. So they are global minimums, they're also local minimums, but what is more valuable to say? It is the lowest in a neighborhood, or it is the lowest the function will ever achieve. It is more significant that they're global minimums, so that's all we label them as. So we then turn to the question, do we have any local maximums? And it turns out, yes, we can see one, right? This function kind of has a hill, a peak of 10 at x equals, and the way that I drew it looks like it's x equals 0. So we sometimes, as long as the graph is drawn nice enough, right, we can identify and classify extreme values just by looking at the graph. But again, this example goes to show sometimes we will have multiple global extrema. It's just that there's really one actual output that is that global extreme value. It happens at multiple coordinates. There is one global minimum, but there are two points that correspond to that global minimum. Negative 2, negative 5, and positive 2, negative 5. Okay, so There's one more example that is worth working out here um, that is actually going to be pretty similar to this parabola that we drew, but I'm going to make one tweak to it, and I want to find and classify extrema of the absolute value of x squared minus 25. So let's find and classify extrema of f of x equals the absolute value of x squared minus 25. So the thing to do whenever we see absolute value functions in a calculus setting is we generally want to take derivatives of stuff, right? So writing out the absolute value as it is, it's a little bit confusing. But maybe if we identify that the absolute value can be thought of as a piecewise function, then that can help us. Well, the truth, right, is that the absolute value of a number is going to be, well, if that number is positive or 0, right, I don't need to change the number at all. The absolute value of 0 is still 0, the absolute value of 1 is 1, 2 is 2, so on and so forth. But if x is less than 0, what does the absolute value do? Well, if I have negative 1, we want to flip that to positive 1. If I have negative 20, I want to flip that to positive 20. So what is one operation that I can do to a number to change its sign? Well, that's just multiply it by a negative. So really, we can think of any absolute value as a piecewise function based on this. So really, f of x is x squared minus 25 if that value, x squared minus 25, 25, is greater than or equal to 0. But then we are going to multiply that by the negative sign, so get negative x squared plus 25 whenever x squared minus 25, that thing we plug in, is less than 0. Well, if we're confused about why I include or equal to on the positive or the negative, it actually in this case doesn't make a difference, right? Because if x is equal to 0, if what I plug in is equal to 0, then multiplying by a negative sign actually doesn't even do anything, right? Negative 1 times 0 is still 0, so negative 0 just is still 0. So in this case, I kind of get to write or equal to on both pieces, right? Because this is a nice function. Right? Absolute value isn't too crazy of a piecewise function. However, we do really want to rewrite these conditions, right? To rewrite when x squared minus 25 is greater than or less than 0. Well, the thing to do here is identify when is x squared minus 25 equal to 0. Well, we can do that either algebraically or by factoring. So, well, I guess factoring is algebra, right? But if I factor this as x minus 5 times x plus 5 equals 0, then I maybe see right away that my two x values are negative 5 and positive 5. Or, heck, I could even add 25 to both sides of that function, or the equation. X squared equals 25, take the square root of that, and get plus or minus the square root of 25. Well, hey, square root of 25 is 5. Okay, so, oh, did not mean to write the square root around 5 still. The square root of 25 is 5. Very good. So, at this point in time, I know that my function hits the x-axis at negative 5 and 5. Well, why do I care about this? Again, I want to know when my function is above 0 or below 0. Well, looking just at x squared minus 25, I know that that is an upwards facing parabola. So I know it has to look like this, right? So I could do more investigation with this kind of function, but I also know it's an upward facing parabola. However, let's actually do that kind of investigation. Let's say I didn't know what sign I was supposed to be. Well, if I know I'm this nice continuous function, and again, I'm investigating x squared minus 25, not the absolute value quite yet. I'm this nice and smooth continuous function that hits 0 at two coordinates, at these two x values. Well, if I want to know where I'm negative and positive, I really just need to know if I am negative on any part of this function, right? Because if I am a negative value, then how do I switch over, right? If I am negative here, how do I switch over to be positive here? Well, if I'm a nice continuous function, I have to cross the x-axis somewhere. So I have to have a 0 in between. So the only way for me to switch signs is to cross over 0. So this means that because I know my function is negative 5, sorry, is 0 at negative 5 and positive 5, there's no way that I can change my sign at any value except there at negative 5 and positive 5. So I really only need to classify, right, figure out what the sign is on each interval, because there's no way that I could change sign anywhere else but when I cross over those intervals. So I need to figure out, is x squared minus 25 negative or positive to the left of negative 5? Well, let's plug in something big like negative, but to the left here, like negative 10. Well, if I have negative 10 squared, oh, there we are, negative 10 squared minus 25. Well, negative 10 squared, negative times a negative is a positive, and 10 times 10 is 100. So this is 100 minus 25, which is 75, which means my function is positive on this interval. Now, if I plug something in between negative 5 and 5, like 0 is a really nice number, well then I see 0 minus 25 is negative 25, so I'm negative on this interval. Well then we can make a good prediction, right? If I plug some positive number greater than 5 in, something like 10, into this function, 10 minus 25 is, sorry, 10 squared minus 25 is 100 minus 25, which is 75. So I have to be positive on this interval, which really means the only place that I am negative, my function x squared minus 25 would be negative, is on the interval from negative 5 to 5. And then I'm positive everywhere else. So for that reason, I get to rewrite my condition. Instead of just saying the x squared minus 25 is less than 0, I know exactly on what interval that happens on, right? This means x has to be between negative 5 and 5. So x is less than 5, but greater than negative 5. And similarly, I'm then positive everywhere else. So if I am to the left of negative 5, right? So if x is less than negative 5, or x is greater than positive 5. So this is how we can rewrite these simple parabolas, or really any function, as a piecewise function, the absolute value of this function into a piecewise function. Very good. Well, why did I do all that? Well, now that I'm a piecewise function and I have it written like this, I'm going to be able to take the derivative of this piece. So, obviously you don't want to erase your sketch work, but giving myself some space to work here, I can now look at this piecewise function and try and take its derivative. So this means that, well, and I had or equal to on this on these pieces, right? But also absolute value of 0 is 0 on either end, right? Negative 0 is still 0, so that's fine. So when I take my derivative, I am also going to have a piecewise function. So for the top part, I want to take the derivative of x squared minus 25. Well, the derivative of x squared is 2x, derivative of negative 25 is 0, so that's just going to be 2x. Well, the derivative of the bottom piece, what is the derivative of negative 2x? What is the derivative of negative x squared? That is negative 2x, and then plus 25, derivative of 25 is 0. Great. So now the catch is on what intervals does this happen at? Well, this derivative, right, happened at the top piece where x was less than negative 5 or greater than positive 5. And this happened when x was instead between those values. However, we have a tiny catch here, right? The derivative is really a limit, right? But when I say these limits, they're supposed to be two-sided limits. So the derivative as x is on the right side of negative 5 would look like negative x, would look like negative 10 on the right of negative 5. But then on the left of negative 5, we have to look up here and we would be positive 10. So my two-sided limit doesn't exist because the left-hand limit would be 10 and my right-hand limit would be negative 10. So because they don't agree, my two-sided limit does not exist, which means I don't get to say or equal to on either part. And the same happens, right, for positive 5 as well. For positive 5 on the left, I would be negative 10. Wait, yeah. Oh, I made a mistake. Sorry. These signs should be switched, right? If I'm on the left of negative 5, I'm looking here, plug negative 5 into this, I get negative 10. If I'm on the right of negative 5, we look like we're on this interval, I plug negative 5 into negative 2x and I get positive 10, right? So because they don't agree to the left and the right, then my two-sided limit doesn't exist, so my derivative doesn't exist at negative 5 or positive 5. And I only showed the work for negative 5 right there, but the exact same argument kind of happens at positive 5 as well. So maybe I even make a point, right? My piecewise derivative is 2x there, negative 2x on this interval, and then just to make it extra clear, I'm going to write for us, it does not exist when x is equal to negative 5 or x is equal to positive 5, just to make it extra clear, right? Even technically by leaving out what x, right, the case, then I'm telling you it must not exist because I didn't say what the output was at either of those x values, but I'm just making it extra clear, right? So now we want to find critical values uh, by looking at our derivative, right? We're wanting to find extrema, so for that reason we look at critical values. Well, we remember that is when the derivative is equal to 0 or does not exist, which is my whole point in kind of emphasizing this question with the fact our derivative doesn't exist at these two values, because we do have critical values where the derivative does not exist. So for that reason, for the does not exist reason, we automatically see x equals -5 and +5. Now when is our derivative equal to 0? Well, we have a piecewise function, so we can look at each piece. When is 2x equal to 0? Well, when x is equal to 0, well, is an x value of 0 in this interval? No. So we move on. When is the second piece equal to 0? -2x equals 0. Well, hey, that also leads to a result of x equals 0. Does that happen in this interval? Yes, it does. So we do genuinely get a critical value when x is equal to 0. But we want to be careful which piece we are actually looking at. So now that we have these three critical values, we want to figure out which of those are local or global extreme values. Well, for one, we kind of have to look at the general behavior of the function at large to figure that out exactly, right? So I'm going to plug these values into my function, right? What is f of -5? Well, that's the absolute value of -5 squared minus 25. Well, hey, that's the absolute value of, oh, I got ahead of myself, -25 squared is positive 25 minus 25. Well, hey, that's the absolute value of 0, which again is just 0. Well, hey, if I plugged in positive 5 for that other critical value, and that's 5 squared minus 25, which is still the absolute value of 25 minus 25, which is just going to go back to 0 yet again. Now, let's plug in f of 0. Let's plug 0 into this function. 0 squared minus 25. Well, that's 0 minus 25, so that's -25, and the absolute value of -25 is positive 25. So these are all of the y values. By looking at my function and understanding it, can I classify these? And I'm going to say, yes, we can, right? Because the absolute value function is the thing happening on the outside. Is it possible to get a negative number out of an absolute value? No. So the lowest the absolute value can ever go is if the absolute value reaches 0. Well, it does that. The absolute value does attain a value of 0 at these two x values, x equals -5 and +5. So we have global minimums of 0 at two x values, -5 and +5. Well, now, can we figure out what's happening with the other critical value when x is equal to 0? That output is 25. Can we understand what's happening there? Well, is there any limit to how large our absolute value can ever be, right? If I take an absolute value of a huge number, hey, that's still going to be a huge number, right? And x squared minus 25 can still be a really, really huge number. So we would say that this function to the left and right increases with that bound. So does this function achieve values larger than 25? Yeah. But is it going to be a local max or min at 0? Well, yeah, if we understand parabolas, their shape is like this. And we looked right there. However, and I'm kind of spoiling some things that'll happen later on, is this going to be a local max or min? Well, this is a normal parabola, but when we take the absolute value, anything that is below the x-axis is getting flipped upwards like this. So we found a critical point right there, Is that a local minimum or maximum? Yeah, it is going to be a local maximum. And what is that value? 25. What is the x value there? 0. So we have a local max of 25 at x equals 0. And this is what it looks like, right? This would be my x squared minus 25, and this is what the absolute value of x squared minus 25 looks like. Well, maybe there's another way to figure out how to find local extreme values even if we don't know exactly what the whole big picture of the function looks like. Even if I can't draw the entire function everywhere, can the derivative tell me something about where local max and minimum values have to be? Okay, so one last thing that I do really want to emphasize with this graph and the derivative not existing is by when we look at the picture of this graph, right? Again, we start with just our nice basic parabola, and right, we have this graph, but then the absolute value says whatever is negative needs to become positive, so this really just gets flipped, right? So we flip that part up, right, and erase everything that we had down here. So this is our graph. Well, does it make sense for our derivative to not exist right here and right here? Well, yeah, we have those jagged edges that happen, right? It looks like this and then this. What is the slope of the tangent line, right, where I can't even really draw a tangent line, right? This pointy bit is too sharp to figure out where to put the tangent line, so that derivative just can't exist, right? So that makes sense from the two-sided limit perspective, but also visually speaking, we should be able to interpret those jagged edges as places where our derivatives just can't exist. Okay, that's the last thing that I wanted to say there. And